Thank you for the invitation to give a talk at this great seminar series. I'm very happy to talk about machine learning for electronically excited states of molecules. And before I'm going to start, I wanted you to think about what would happen if there was no light. So I believe that every one of us could think of at least one thing that would not exist without light excitation. And indeed, many fundamental processes that are fundamental to nature and the life form we know depend on light excitation. Take, for example, photosynthesis, human vision with the eye, or phototherapy. All these processes depend on light-induced reactions. But there are also negative side effects of such type of reactions. Those are, for example, skin alteration and skin cancer, bleaching, or blindness could also be a result of light-induced reaction. And in order to understand why these processes take place in the way they do, and in order to understand why the photochemistry happens in the way it does, we need to take a look at the smaller building blocks which can absorb UV or visible light. And if we want to study the photochemistry of the molecule, we might first ask ourselves if the molecule can actually absorb the light and can use the energy. So consider a molecule that sits in its electronic ground state. It can't move on this ground state potential energy surface. But when light enters, the processes become much more complicated because now a lot more potential energy surfaces become accessible. And as you can see, we now have two excited state potentials. And if the molecule can absorb light, the next question is which electronic state does it enter? So to which electronic state is it excited? And we can find an answer to this question by taking a look at an absorption spectrum. So you can see here that the absorption is plotted against the energy that hits the molecule. And there are two peaks, one is small and one is large. And the large peak shows that the molecule is very likely to be excited to this state. And this state here corresponds to the second excited state. So by taking a look at an absorption spectrum, we can find out that the molecule can be excited to the second excited state within a given energy range. After we know that, we want to know what processes take place after the light excitation. And we can get an answer to this question by studying excited state molecular dynamics. In excited state dynamics, we just follow the motion of the molecule on the excited state potential. And whenever two potentials are close to each other, there can be transitions from one state to another. And those transitions are dependent on the coupling between the different potential energy surfaces. And if we know which type of transition happens, we can explain whether a molecule is photostable or not. There is a very efficient method with which we can do excited state dynamics, and this is called surface hopping molecular dynamics. It is a mixed quantum classical method where the nuclei are treated classically and they move on a potential energy surfaces that are made up by the electrons, and the electrons are treated quantum mechanically. So let's again take a look at a molecule that is excited to a higher electronic state, and we want to follow the motion of this molecule. And what you can see is that there is a transition from one state to another. And this transition is called hop within surface hopping, and it is determined stochastically. So due to the stochastic nature, we do not only want to excite one molecule, but we want to sample a lot of different molecules and excite them. And we then want to follow the motion of the many molecules in order to get different reaction channels and get different branching ratios. So it all starts with a molecule that is excited. And we use electronic structure theory to compute the energies, the forces, and also the couplings between the potential energy surfaces. These electronic properties can then be given to a molecular dynamics program. Here we use the program SchNarc. It stands for surface hopping, including arbitrary couplings, and it was developed at my former research group at the University of Vienna, in the research group of Letizia Gonzalez. So this dynamics program can take the electronic properties that we computed with quantum chemistry, and it can use this information to classically propagate the nuclei of the molecule. So this is how we get to the dynamics. We just do the simulations a lot of time until we have a long enough dynamics. But there is one problem in this process, and this is related to the computation of the electronic properties, because it is very expensive. And this is not only the case for the dynamic simulation, but it also starts when we want to know if the molecule can be excited. So let's go one step back to the first thing that we want to find out, whether the molecule can absorb light or not. So if we want to get an accurate absorption spectrum, then we need to sample a lot of different conformations of a molecule, and we need to compute the energies and the dipole moments in order to get the absorption spectrum that we can also compare to experiments. So we need the energies and the dipole moments because the intensity is related to the energy gap and also to the transition dipole moment between two states. And this molecule here is called the methylenimmonium cation, and it will be the test model throughout this presentation. So in order to get these 1,000 calculations done and to compute this absorption spectrum, it takes about 1 day on a CPU for this molecule with an accurate quantum chemical method. This is quite okay, and one can argue that all these 1,000 calculations can be sent at once, so it might take only a few hours to compute. But imagine we don't only want to investigate this one molecule, but we want to sample across chemical compound space, and we want to investigate the spectral fingerprints of these molecules and differences. So what happens if we replace the nitrogen atom with a carbon atom? Or what happens if we remove a hydrogen atom? So if we want to also sample across chemical compound space and want to compare thousands of molecules, doing 1,000 calculations in 1 day clearly becomes a bottleneck. And this is even more severe when we take a look at surface hopping molecular dynamics. Let's again take this molecule. It contains 6 atoms. And a multi-reference method, which is most often the only viable accurate method for excited states, takes about 2 days in order to simulate 100 femtoseconds. And 100 femtoseconds is not so long. Now we are already here in this seminar for a couple of minutes. So, and if we want to do, for example, 1 nanosecond, which is also not that long, but a lot longer than 100 femtoseconds, it would take us about 19 years to compute on a supercomputer. So this is clearly out of reach. And if we now want to investigate biologically more relevant systems, such as an amino acid, here you can see tyrosine, it contains 24 atoms. The computation of 100 femtoseconds would take us about 291 days with another multi-reference method. So electronic structure theory is expensive and we want to get rid of it. And we do this by using machine learning. So what we want to learn is we want to learn the electronic properties that are computed with quantum chemistry in order to get efficient absorption spectra calculations and surface hopping dynamics. So therefore, we have developed a machine learning model and implemented it into the SchNarc approach, and this is called SchNarc. So obviously, it is a combination of the molecular dynamics program SchNarc and a deep learning model, which is a neural network, and it is called SchNet. This was developed at the Technical University of Berlin. And we adapted this model for the excited states, and together it makes SchNarc. So what can we do with it? We can fit excited state energies and the derivatives of an arbitrary number of states. We can describe singlet and triplet states. We can also fit the couplings between the electronic states and the dipole moment vectors in order to get efficient absorption simulations, photodynamic simulations. And because we have the potential energies, we have the derivatives, we can also do geometry optimizations, and we can also search for critical points on the potential energy surface. Throughout this presentation, the methylenimmonium cut ion will be the test system, and I will show all the developments that we have done with this molecule. Why have we chosen this system? So it is on one side very small, so we can use a very accurate reference method in order to describe the processes really accurately and to have something to validate the machine learning model for. So we have chosen the multi-reference configuration interaction single-double method, which is a very accurate method with a double zeta basis set, and we described 3 singlet states. We have also chosen this molecule because it can be excited to the second excited singlet state, and it shows ultra-fast population transfer within 100 femtoseconds. So this plot here is the ultimate goal that we want to reproduce with machine learning. It shows the population of the molecule in every electronic state. This is plotted against the time. So you can see at time 0, all of the population is transferred to the second excited state. And we first of all want to reproduce the excitation. And then we want to also reproduce the ultra-fast population transfer. Within about 20 femtoseconds, half of the population is already transferred to the first excited state, and within 100 femtoseconds, almost all of the population is transferred back to the ground state. And this is quite challenging to reproduce with machine learning. The machine learning model behind SchNarc is a neural network. I'm sure that most of you are very familiar with this concept, but I will still shortly explain. So a neural network was originally developed to mimic our brain. So just as we want to learn, the machine learning model needs to learn something. And here we learned the relation between a molecular geometry and the electronic properties. Therefore, we need to transform the molecular geometry in a rotationally and translationally invariant descriptor, which means that if the molecule sits here or it sits here, it should not matter. It should always give us the same energy. And the neural network then tries to find the best parameters that relate this molecular structure, the descriptor, to the electronic properties. So what we want to describe are the ground state energies, the excited state energies, and other properties. In order to learn this, we need a training set which contains both the input and the output. And it is not always so easy to generate a meaningful and comprehensive training set, especially if you don't know what conformational regions you need to represent with this training set. And on the other hand, because electronic structure theories, so many quantum chemical methods for the excited states are very expensive, the training set should be as small as possible. So we started by sampling the molecule along the normal modes of, so for example, the stretching mode and also the rotation. And with this, we could sample a small conformational region around the equilibrium structure of the molecule. We then tested if the data points were already enough. So we trained a machine learning model, and we did then surface hopping dynamics. And as you might imagine, we will soon enter a region that the machine learning model has not learned before. And what will happen? It will do something which should not be the case. So the molecule starts to fall apart, which will hopefully not happen in reality. So we need a better way to sample the data points, and therefore we have adapted the adaptive sampling scheme that was originally developed by Jörg Behler for ground state dynamics, and we adapted it for the excited state. So we can start with our initial training set, and now instead of training one machine learning model, we train 2 machine learning models. And then we again do the dynamics. But now we make use of the fact that machine learning models are very good in interpolative regions, but they fail to extrapolate to unknown configurational space. So every time step during the dynamics, we compare the predictions of two machine learning models. And as soon as they start to diverge, we know that we have entered an unexplored region. So when our models diverge, we can do a reference calculation. We can take this data point, give it to the training set, and then we retrain the two machine learning models. Well, as you might think, this can get quite expensive because training is also not for free. And therefore, as also many others in this field, we do not do one machine learning dynamic simulations, but we do hundreds of dynamic simulations, and we wait until every dynamics has entered an unexplored region. So in this way, you can get a lot faster towards converged machine learning potentials. Unfortunately, there is still one problem, which is only related to excited state properties that are from two different electronic states. So I want to explain this problem to you by taking a look at molecular orbitals. So the problem is related to the phase of the wave function because the phase is not uniquely defined. This is very similar to having either a blue orbital or a red orbital, which could be associated with a plus sign or a minus sign. So if we want to calculate, for example, the energy of state I, the wave function of this state enters twice in the equation. And we all know that +1 times +1 and -1 times -1 is +1. So we should always get the same sign for the energy. But when we want to calculate off-diagonal elements in terms of matrix notation, such as coupling vectors or dipole moments, transition dipole moments, the wave function of two different state enters. So here you can see of state I and J. So the phase, the color or the sign doesn't necessarily need to cancel out. It could be that we have either twice a blue color or red and blue, and this is not the same. So we can either have a positive sign or we can have a negative sign of the dipole moment. And a machine learning model has problems to fit a value that is not uniquely defined and can arbitrarily switch the sign. So therefore, we have developed a phase-free training algorithm. So we don't know which sign is the correct one. Either we have a positive sign or we have a negative sign. And the machine learning model also does not know. But what do? We once assume that we have a positive sign. So we compute the error with respect to a positive sign and give it to the machine learning model. And then we compute the error and we take a negative sign. And we train the machine learning model by taking the minimum of both of these values. So with this, we can kind of sort the right phase at every training iteration. And this makes the training independent of the sign of the coupling values, and it makes training on raw data possible. So we have then developed all the processes. We can now generate the data, and we can train them in a phase-free way. So we can train energies, and we can also train the coupling values and other properties that result from two different states. But now we need to investigate is it better to train a machine learning model on all of the different properties simultaneously, or should we take one neural network per excited state property? And we've analyzed this and came to the conclusion that it is beneficial to use one neural network for energies and gradients and one for every other property. And then again, because we have more electronic states, we could either train one machine learning model on every electronic state separately, or we can use one machine learning model and train all of the states simultaneously. And this is what we did in our study. So we developed the multi-state machine learning model. So with this, we could train the energies, but now the dipole moment is a vector, and it points into a direction. So this means if we have our molecule, here you can see the example, this is the example of water, and you can see that the dipole points towards the oxygen. And if the molecule rotates, the dipole moment should rotate with the molecule. And therefore, we cannot simply fit every value of the dipole moment vector, but we need to describe it in a rotationally covariant way. So we need a way to include a vector in the fitting scheme. And there is a model that was already developed for the permanent dipole moment of the ground state. So we again could very well use a model that was already developed for the ground state and can adapt it for the excited state. So what we want to learn are the dipole moments, so the permanent dipole moment of one state or the transition dipole moment between two states. And the dipole moment can be expressed as the sum of atomic partial charges Q. And this can be multiplied with the vector from this atom to the center of the mass. And because we have the molecular structure, we know this vector, but we do not know the charges. And we still fit the dipole moment. So we let the machine learning model build an artificial partial charge, and we multiply this artificial value with the vector from the atom to the center of mass and map it to the dipole moment. So in this way, we can learn the dipole moments rotationally covariant, and without the machine learning model having ever seen an atomic partial charge, it can still try to find a meaningful value, or I will show to you soon. So this is the first result that I want to show you with our developed method. You can see on the left, this is the absorption spectrum that you have already seen before. So you can see that the orange peak is rather small, but the dark red peak is rather large and is related to the second excited state. And on the right side, you can see the machine learning prediction. And you can see that it matches the reference spectrum quite well. The computation of this reference spectrum, so for about 500 calculations, it took us about 16.7 hours on a supercomputer, and one calculation took about 2 minutes. And with SchNarc, this was trained 11 hours on a GPU. We could do 500 predictions in about 10 seconds, and one prediction takes about 20 milliseconds. So there is a huge speed up if we need to do many more calculations. Yes, I've mentioned that we can get the partial charges for every atom. So I showed to you now the electrostatic potential that is built from the partial charges that the machine learning model has never seen before. And you can see that in red, there is the negative charge, which is located closer to the carbon atom, and the positive charge is located closer to the nitrogen atom. Here is a comparison to the Hirschfeld charges, and you can see that also here the negative charge is located closer to the carbon atom and the positive charge closer to the nitrogen atom. So, of course, the charges should be interpreted with care, but still they give you a qualitatively correct trend. And we have the excited states as well. So we can compare the charge distribution that the machine learning model finds from the ground state towards the excited state. So you can see that on the left, the charge is located quite really on the left, and then it moves towards the center. Okay. So what I have not shown you before is that here is the machine learning prediction, but there are also dashed lines. And the dashed lines are from a machine learning model that was trained not only on the methylenimmonium cation, but it was trained on another molecule. And this is ethylene. So instead of a nitrogen atom, we now have here a carbon atom. And we trained the machine learning model on both molecules. So we generated the training set of this model by just taking exactly the same data points and replacing the nitrogen atom with a carbon atom. And we trained the machine learning model on both molecules and predicted the UV visible absorption spectrum. And you can see that compared to the methylenimmonium cation, ethylene has a very broad peak that corresponds to the first excited state, whereas the absorption peak of the second excited state is rather small. And this behavior can be also predicted with machine learning. So we could train a machine learning model on two different molecules and get the excited state characteristics of these molecules. So we also wanted to investigate whether we can go to systems that the machine learning model has not seen before. And here we removed the hydrogen atom and predicted the spectrum. And you can see, although there are some dissimilarities, it gets a qualitatively correct spectrum. So between 6 and 8 eV, you have a very high chance that the molecule is excited to the second excited state. And we also removed the hydrogen atom from the carbon atom. And you can see that the peaks shift a little bit and they overlap more. And this behavior can also be predicted with machine learning, although the model has never seen these molecules. So with these results, we concluded that at least for similar molecules, machine learning models can be transferable through chemical compound space. And now that we have developed the machine learning model and could investigate the absorption and now can also reproduce with machine learning that the molecule can be excited to the second state, we also want to find out if we can do surface hopping with machine learning. So I've shown to you this population plot before, and with machine learning, we wanted to reproduce the excited state dynamics. So the solid lines show you the predictions with the machine learning model, and the dashed lines are with quantum chemistry. And you can see that we can reproduce the population very well. So this goal we have met. We also now can do a lot more calculations because machine learning is much cheaper than quantum chemistry. So we get a lot better statistics. Take, for example, a very rare event that happens. So one molecule in about 1,000 takes another path. And now we are allowed, we can sample a lot more trajectories. And we can also investigate rare events if we use, if we compare machine learning models all the time and investigate whether we enter an unexplored region. And what is more is that if we do a lot more trajectories, we can get smoother population curves. So machine learning is more efficient than quantum chemistry, and with quantum chemistry, it is not possible to go to really long timescales. So we wanted to investigate if we can go to long timescales that are beyond the feasibility of the reference method and predict 1 nanosecond simulation. And here I show you the dynamics with machine learning for 1 nanosecond. And you can see that after about 200 to 300 femtoseconds, all of the population is transferred to the ground state here. But we can still simulate for 1 nanosecond. And this is was about 118 times faster and was feasible within 59 days. Whereas with the reference method, it would have taken us 19 years, which would have not been possible in my PhD. So we can also go to long excited state dynamics. And there is still an open question, which I cannot answer to you. And this is if we can also develop machine learning models that are transferable for the excited state dynamics. So there's still a lot of development going on regarding the excited states. And I'm sure that there is a lot more to come. So to conclude, with the SchNarc approach, we developed a machine learning model for excited states of molecules where we can describe excited state energies and properties, especially coupling values and dipole moments. And we have shown this for the methylenimmonium cation, ethylene, and also the spectra for very similar molecules. We have implemented an efficient training set generation, which called adaptive sampling for excited states. And with all the developed methods, we can do machine learning accelerated visible absorption spectra calculations and sample many thousand molecular structures. And we can also do efficient photodynamic simulations. And with this, I want to thank my former supervisors, Philippe Macroton and Letizia Gonzalez, and my current research group at the University of Warwick and Dr. Reinhard Maurer. And I'm happy to answer any questions.